Assalamualaikum warahmatullahi wabarakatuh and good morning to everyone. My name is Nur Sakina and I will be presenting on the project with title of Automated Segmentation of Woodball Swing and Faces from Inertial Measurement Unit. This project was conducted by myself, Nur Sakina binti Maisam, and Associate Professor Engineer Dr. Ahmad Faizal bin Saleh and Professor Dr. Muhammad Yusuf bin Mashur. So in 1919, the woodball was invented in Taiwan and was categorized as an outdoor activity according to the International Woodball Federation. Later on 1992, this activity was officially named as woodball. Woodball is a sport where a mallet is used to pass a ball through gates. This game can be played in grass, sand, or indoor and can be played in the single, double, or a team of 4 to 6 player format. Woodballs require minimal equipment. Unlike golf, only 3 pieces of equipment are required to play woodball, which are wooden ball, mallet, and gate, which are shown in Figure 1. To our knowledge, there were no documentation on the swinging phases in woodball. According to woodball experts and coaches, woodball and golf require almost similar playing skill. Hence, it is safe to assume that both golf and woodball have same swinging phases. A full swing with mallet motion was divided into 5 phases, which are before swing, back swing, downswing, follow through, and after swing. The swing was later split into 4 dividing events, which are address, backswing top, impact, and finish as in Figure 2A. Figure 2B shows the velocity signal of the swings, and based on this reference, the swing signal obtained from the subject will be processed and segmented into 4 phases. One of the popular wearable monitoring systems is Initial Measurement Unit or IMU, which has been shown in Figure 3. This device is light, small, and cheap, and also proven to be provide useful statistics and information from athletes. IMU is a device that consists of multiple sensors such as accelerometer, gyroscope, and magnetometer. This device is specialized in measuring boost angular velocity and acceleration on 3 axes in space, which output from the gyroscope and accelerometer respectively. So this project is mainly focusing on the sport analysis on woodball. Sport analysis is the field or event carries on subjectively analyzing movement to optimize a skill or technique of sportsmen. It allows athletes to take a critical look at their performance in order to improve skill and prevent injury. IMU has the potential to be used in the creation of a system that can assess the woodball swing. Before performing the real movement analysis, it is necessary to determine the movement phases and event. Generally, amateur woodball players have difficulty in practicing their playing stances and swing mechanism without any coaching advices, especially for those who are unable to pay for high fee. With the lack of any supervision from coaches, this player may unconsciously repeat the incorrect posture of their swing mechanism. Hence, it was crucial to have a system which can measure their swing technique quantitatively and giving scientific feedback to improve their skill. Therefore, a primary goal of this project is to study the movement phases in woodball swing using IMU and create a system that can help with the coaches and athletes to analyze their swing. To create a system which is capable of analyzing the woodball swing, it is important to identify suitable filtering technique as the first step in signal processing to filter the unnecessary noises in the signal. Later, the filter velocity of the swing signal will be modeled using IMU by utilizing a classical mathematical regression analysis called the square method. After modeling, the swing phases will be segmented into their respective phases and the performance of the modeling will be evaluated. So in our project, this is the second version of the woodball sensor. Table 1 shows the difference between version 1 and version 2. In version 1, we make use of the data from both IMU sensor and optical motion capture system or OMCS, which is collected inside a laboratory. Meanwhile, in version 2, we only utilize the data from IMU sensor, which can be attached to the player's wrist and the data can be collected anywhere. For the model validation technique, version 1 used one step ahead or OSA prediction and version 2 used model predicted output or MPO. Woodball Swinzer version 1 produced a result with high accuracy percentage of more than 95%. Meanwhile, version 2 produces a result which is slightly lower than version 1, which is above 85%. Before using the system, user need to have both IMU and OMCS data in version 1. In contrast, only IMU data is needed in version 2. So the GUI, the graphical user interface system of both versions are shown in the slide. So here is our methodology flowchart. The flowchart consists of data collection, signal processing, modeling, segmentation, and performance evaluation. Generally, the procedure starts by collecting some data from Woodball's player. The IMU signal obtained from the player will process using butterworth filter, estimated using least square method, and the swing event will segmented and the model performance will be evaluated. So for data collection, the signal data were collected from 30 Woodball players by using both IMU and OMCS. IMU was positioned at the player's left-hand wrist and retro-reflective marker for OMCS were placed on top of the IMU and the mallet as in figure 4. In the experiment, OMCS was used to measure the acceleration and resultant linear speed of the swing from player's left-hand wrist and mallet. For validation of the data from IMU sensor, the resultant linear velocity obtained from OMCS was used as a reference due to their similarity in envelope and shape of the signal based on our observation as presented in figure 5. So data from both IMU and OMCS were filtered using signal processing method called butterworth filter. Butterworth low-pass filter will remove the high-frequency noise from a digital signal and preserve the low-frequency components. The parameter of IMU which used as a feature of the swing motions are angle, angular acceleration, and angular velocity and acceleration. Figure 6 shows the frequency response of butterworth filter with the orders number. In theory, the higher the number of filter order, the more ideal the gain curve will be, but the currency of the filter will be decreasing. So, least square is the most typical statistical regression method used to find the best curve or line through the observed value and minimize the residual sum of square or error as illustrated in figure 7. Least square is a very easy to use and simple, hence making it the most reliable method to be applied in the analytical analysis. Signal segmentation is crucial to divide a signal to several epochs with the same statistical characteristics such as amplitude and frequency. The method used in this project is called as peak detection technique. It is important to identify and analyze the peak in a time series signal as it is one of the most useful topological features of a time series. The maximum peak of the swing signal will be automatically detected by the system and labeled as impact, while the value will be labeled as backswing top. By using the value obtained by the backswing top, the beginning and the end of the swing will be labeled as the address and the finish respectively. The performance of the model will be evaluated using model predicted output, which is proven to provide better measurement on the capability of the fitted model predictive. The accuracy of each basis will be calculated based on the formula in the slide. So here is our result. After the data was collected, the signal will undergo signal processing. In here, the signal will be processed and filtered using second order butterworth filter. The IMU signal was tested with cutoff frequency of 5 Hz, 10 Hz, and 15 Hz as shown in figure 9. And 10 Hz provide the best result as it is able to remove unwanted noises but still able to maintain the envelope of the signal. Figure 10 shows the difference between raw and filtered resultant IMU parameter. The notable changes of each parameter were highlighted in the red box. The filtered signal will then be modeled using least square method. The number of the least square order again mean square error is plotted as in figure 11. Theoretically, the further the value of mean square error from origin, the better the model will be. From here, we can see that at order 3, the value of mean square error for both x-axis and z-axis are at the lowest. Hence, the order of 3 was selected for the model. So figure 12 shows the estimated IMU signal which has been undergoes modeling process and the resultant velocity at mallet which is collected from IMCS. The blue line indicates the estimated resultant velocity of IMU, while the red line is the resultant velocity obtained from the OMCS. Here we can observe that the least squared model was able to model the resultant velocity signal and produce almost similar shape and envelope as from OMCS. Moreover, figure 13 shows the system is able to segment and label the estimated IMU signal accurately, which is now mapped with the velocity signal from OMCS. The performance of the model was evaluated and tabled to present the accuracy percentage of each dividing event. It shows that the system able to produce result of more than 85% accuracy. So here is our second version of Woodball swinzer. The system which shows the signal of original Woodball swing, the standard Woodball swing phases, the estimated Woodball swing which is validated using OSA and MPO as in version 1 and 2 respectively, and also the accuracy percentage of each phases. As a conclusion, the data from 30 subjects were collected and the swing signal were processed using second-order Butterworth low-pass filter. Later, the signal were modeled by least squared method, segmented into their respective dividing events, and was validated using model predicted output. The proposed system yielded good classification performance with an accuracy percentage of more than 85% for all swing events. The procedure can be improved by analyzing the swing signal and providing the evaluation on the swing quality in the future. This is all from us. Thank you.